This is the final video lesson for radiographic equipment on X-rays and subject factors. To begin with, we're going to look at the idea that we have the primary beam, which is also called the useful beam. And that useful beam are X-rays that are coming from the tube window. Secondly, as we've talked about previously, we have the absorbed radiation, which is from the photoelectric interaction, where the X-ray photon is totally absorbed. We have scatter radiation, which the photon is partially absorbed and then emitted from the patient. And finally, we have what's called remnant or exit radiation, which is radiation that reaches the image receptor. And so those are just some terms that we want to look at. Let's take a look at factors that affect X-ray quantity and quality. First, let's review that beam quantity is also known as intensity or exposure, and even the number of X-rays. Beam quality is also known as energy or the penetration of the beam. So an increase in MA will increase intensity or exposure, otherwise known as beam quantity. An increase in KVP will also increase beam quantity, while an increase in SID will decrease beam quantity, and an increase in beam filtration will decrease beam quantity. On the other hand, an increase in KVP and filtration both increase beam quality. So if we take a look at mass, less mass versus more mass results in more X-rays in the X-ray beam, first of all, in the primary beam, and it also results in more X-rays that are in the exit or remnant beam. And so it's just going to result in more X-rays reaching the image receptor. And so that's why there's an increase in MA or mass will increase beam quantity. When we look at KVP, a low KVP beam has low energy with long wavelengths, and there's going to be less X-rays reaching the image receptor because there's less penetration. More X-rays will be absorbed in the patient, and therefore there'll be less reaching the image receptor. A high KVP beam has short wavelengths, and it's going to be penetrating the patient, going through the patient, and more will reach the image receptor. So that's going to increase the beam quantity. When we consider beam quality, the term energy is quality. So a high quality beam also has high energy or high quality. When we look at filtration, filtration decreases the number of low energy X-rays that reach the image receptor, and it decreases patient's skin dose. It does not affect the radiographer's dose. Inherent filtration, which is made up of 0.5 millimeters of aluminum, is comprised of the glass and the oil. The added is 1 millimeter of aluminum, and that's just aluminum. And then the mirror in the collimator box is comprised of 1 millimeter of aluminum equivalent as well. So filtration is something that's going to decrease the number of low energy X-rays, and it's going to result in less X-rays. So we have 13 X-rays before the filtration, if we count them across, but we only have 6 after the filtration. But these X-rays down here, the 6 that are down here, have higher energy because we lost the low energy photons. So subject factors, we have radiographic contrast is equal to image receptor contrast versus subject contrast. It's a direct result of differences in attenuation in body tissues. So attenuation, that by definition is a reduction in the total number of X-ray photons remaining in the beam passing through a given thickness of material. So if we look at the number of X-rays before they go through the patient as the useful beam or incident X-rays, there's going to be more of them. There'll be less that make it through the patient. And that's called attenuation, reduction in the total number of X-rays as they traverse the patient. So that reduction in X-rays remaining in the beam after passing through is due to a few things. It's due to an increase in part thickness, it's due to an increase in tissue density, and it's due to an increase in atomic number. Now it's a result of photoelectric and Compton interactions because photoelectric and Compton are absorption. Photoelectric is total absorption and Compton is partial absorption. So there are a number of factors that affect subject contrast, and we'll take a look at these right now. So the first item is patient part thickness. A thicker body part attenuates more X-rays than a thinner one. We can see that on the technique charts here with the fixed KVP system, that even with fixed KVP, we have to increase the mass as the body part increases in size. The same thing happens with a variable KVP chart where the mass stays the same. As the body part increases, the KVP had to increase. So just looking at, we need to compensate for that increase in attenuation. Here's an example of film screen radiography with a smaller part where 55 kVp at 1 mass was used, and then where a thicker part, such as a skull, the exact same technique was used, the larger part decreased receptor exposure visibly. Additionally, a larger part or patient will also decrease image contrast. Why? Well, the same, more matter, more scatter. So the more matter there is, more scatter will be produced. And that's why the image is so gray. Tissue density. So we have low tissue density, medium tissue density, and high tissue density. Tissue density or mass density is the number of atoms or molecules in a given space. And the lower the tissue density, the less likely that the X-ray photon going through is going to interact with an atom or molecule. With a higher tissue density, it'll increase that. So an increase or higher tissue density increases interactions with matter, and that's both Compton and photoelectric interactions. Now, effective atomic number has a great impact as well. If we look at the image on the left-hand side, it's a patient, well, it's not a patient, actually, it's a phantom. But on the right-hand side, we have the barium enema that was performed, and we can see that the area that's so white is the barium. And that's because the atomic number of barium is 56 and has a much greater atomic number, increase in atomic number compared to soft tissue of 7.4. An increase in atomic number increases total absorption, which is photoelectric interactions, by a cubed effect. Remember that total absorption is the photoelectric interaction. KVP is the most important influence on subject contrast. At low KVP, we have more photoelectric than Compton interactions. As KVP increases, we have less photoelectric interactions. In fact, they decrease by a cubed effect. So when we look at the result on the image on the right-hand side, we have low contrast because we have more Compton than photoelectric interactions at high KVP. Body habitus, we know that technique charts are based on sthenic patients. So technique charts need to be revised so that we can actually have an idea of exactly what to use for different size patients. And we should use calipers as a recommendation to use calipers so we know exactly what technique to set as far with manual techniques. Radiopaque materials are those that are going to absorb X-rays. And so radiopaque materials that we can see here on the image in the mediastinum is a great example. Radiolucent materials such as air is something that's going to allow X-rays to transmit through. So composition is going to make an impact on our image as well. In terms of radiolucent versus radiopaque, the radiographic appearance for the asthenic patient would be radiolucent, which is black, and then the hypersthenic would be white, which is radiopaque, in terms of degrees of radiolucency. In terms of composition, we've got the different composition absorbing characteristics of the body. So low subject contrast body parts, such as the breast, has the least subject contrast of any body part we have, but in diagnostic imaging, it would be the abdomen. High subject contrast body parts, upper GI would be really high, especially if we have a double contrast, but a chest x-ray would be a great example also. If we compare the chest and the abdomen, these are both phantom images. The chest has higher subject contrast and the abdomen has lower subject contrast. And what does that mean? It means that the chest has higher contrast, which is more black and white, and the abdomen has low subject contrast, which is more gray. So composition, we have gas, fat, muscle, bone, and metal. And in order, these go in order from more radiolucent to more radiopaque. So the gas is the most radiolucent material, and it's going to be something that's going to be easy to visualize on an image, very dark in the image, and then fat in order, then muscle, then bone, and then metal is very radiopaque. It's very white. So looking at a radiolucent to radiopaque, we've got lung, then fat, then muscle, then bone, going from radiolucent to radiopaque because lung is like air, and then fat, then muscle, then bone is the most radiopaque of our degrees of radiolucency of our materials in our body. So one reason why is because air has an atomic number of 7.78, which is really close to fat and water and muscle, but bone has a much higher atomic number. It's 12.31 if you look in, this is from Carlton and Adler. In Bouchon's textbook, he says it's 13.8. As far as the tissue density is concerned, we're looking at the tissue density having a great impact. So air only has a tissue density 1.29 kilograms per micrometer, the meters cubed, 916 for fat. Water's like right there in the middle at 1,000. Then muscle is 1,040, and then bone is 1,650. So as we increase tissue density, we increase radiopacity. So let's take a look at air. Air has an atomic number of 7.78. It's greater than fat or muscle, but it has a low tissue density, in fact, the lowest tissue density. It absorbs few photons, results in an increased area of exposure on the image receptor, and it is radiolucent. It's going to result in the least attenuation of all of our materials. Then we have fat. It's otherwise called soft tissue, one of the soft tissues. Its effective atomic number and tissue density are similar to water. Its effective atomic number is slightly less than muscle, but fat has a tissue density less than muscle and therefore will contrast with muscle on images. Muscle is another type of soft tissue. It has a slightly higher atomic number and tissue density than fat, and considered a water density. The material in our body that has the most opacity or that has the most attenuation next to metal would be bone. It's composed of calcium and phosphorus salts. Calcium has the highest atomic number of all elements found in the body, and it has the greatest tissue density of the 4 basic tissue substances. It has a very high absorption or attenuation of photons. It has a large percentage of photoelectric interactions. It has a decreased area of exposure on the image receptor and in considered areas that are radiopaque. And here's an image showing air, or number 1 showing air, excuse me. Number 2 showing the kidney, which is the outline of its fat. Number 3 showing the psoas muscles, which have a different density than the fat. Number 4 showing, and a few different number 4s here showing bone. So looking at those 4 different types of materials. And again, the air has the lowest attenuation or least attenuation, where bone has the most attenuation. Contrast agents. So we have two positive contrast agents. They are barium sulfate and water-soluble iodine. They're very radiopaque, and they're going to have a very high attenuation. Negative contrast agent, we refer to air. In this case, we're talking about very low attenuation, just like the lung would be the same, kind of the same concept. So very low attenuation with low absorption. The use of a contrast agent will increase image contrast. So in the image on the left compared to the one on the right, which is the barium minima with the air and the barium, has a higher image contrast. Additive conditions versus destructive conditions. So additive conditions have an increase in fluid, metal, or bone. They increase mass density or composition. The tissue is more radiopaque. There's also an increase in absorption of X-rays. We have a decrease in receptor exposure, and it requires an increase in mass by 50%. Additive diseases are considered something that have a higher attenuation of X-rays. Destructive diseases are those that have an increase in air or gas, or a decrease in normal body fluid or bone. So there's a decrease in mass density or composition. The tissue is more radiolucent. There's going to be a decrease in absorption, otherwise known as attenuation of X-rays, and we're going to see an increase in receptor exposure. We want to decrease mass by 30%. So pathology can alter tissue and composition of a patient's tissue density. On the left-hand side, it's kind of small, but we've got the fluid, the collection of the lungs, which adds to the tissue density. So that would be considered an additive condition. Or on the right-hand side, we've got a person with emphysema, and they have a loss of tissue density due to emphysema, and it is a destructive lung condition, where they have an excess amount of air or overinflation of air. Additive conditions decrease receptor exposure. So if we look at the image on the left, which is the normal, versus osteopetrosis on the right-hand side, osteoporosis has less receptor exposure. On the other hand, destructive conditions increase receptor exposure at the areas of the carpals and the radiocarpal joint, and also the metacarpal phalangeal joints, and even the pips that are shown. We have the areas are darker, so that's an increase in receptor exposure that resulted. In the lesson on radiographic equipment, we went over the term cycle again. We talked about the wave equation, the inverse square law, laws of electrostatics and magnetism, types of materials, factors in electric circuit, the electric current, the generator and motor, and transformers, and then rectification. In part 2, we looked at the X-ray circuit and generators. In part 3, we looked at the X-ray tube. And in part 4, we looked at factors that affect beam quantity and quality, as well as subject factors. And this concludes our lesson on radiographic equipment.